In our last class, we introduced Kirchhoff's current law and Kirchhoff's voltage law. These two fundamental laws in circuit analysis can be used to help solve certain circuits. In today's lecture, we're going to start developing approaches for using KCL and KVL to solve circuits using circuit simplification techniques. Before we do that, however, we're going to briefly talk about another approach to solving circuits called the ad hoc circuit analysis approach that in practice you do not want to use very often. The term ad hoc is a Latin expression meaning for this situation. The idea behind an ad hoc circuit analysis approach is you start using concepts such as Ohm's law, KVL, and KCL to try to solve for whatever desired voltages and currents you have in a circuit by thinking, what do I need to do next? And then writing equations and trying to eventually get to the solution. And what you're going to see in this ad hoc approach is you often have intermediate equations or variables that you need to create in order to try to solve the circuit. And what we're going to see is that even though this ad hoc approach works, especially in simpler circuits, it often leads to more work than necessary. You end up introducing many more equations than you need because it is a very disorganized approach. To sort of illustrate this disorganization aspect of it, let's do one example, and this is a relatively simple circuit, and we're going to see that using this ad hoc approach tends to be a little messy. So once again, I need to stress that this approach is not an approach that we want to use in general. I'm using it here to show that it can work, but also to show that it really is not the best approach. So if you look at the circuit here, this is the same circuit that we saw in the previous example. In the previous example, we were only asked to find two different variables, Vx and Iy. We saw that Vx was fairly simple to find by doing a KVL along this loop here. And we saw that Vx was 8 volts with the plus on the left and the minus on the right. We saw that Iy could be found very easily by doing KCL at this red node here. And we saw that using KCL that the current through this 2 ohm resistor was 2 amps going up. So this is what we did in the previous lecture. In this lecture, we're going to take this a step further. We're asked to find the power supplied or absorbed by each of the independent sources. So in order to find the power absorbed or supplied by each of the independent sources, we need to find the current through every voltage source, and we need to find the voltage across every current source. We can then apply the power equation. So let's define some new variables. So to find the powers, we need to first find the following variables. The first thing we need to find is the current through the 12-volt source. Let's define a new variable. We'll call it I sub 12 volts. This is a current through the 12-volt source. And notice I arbitrarily oriented this current variable going from bottom to top. There's nothing magical about that. I can define the variable however I want. Once I define the variable, however, I need to be consistent in using it. So that's going to be the first variable we need to find. We also need to find the voltage across the 6 amp source. So once again, I can be arbitrary in how I define the plus and the minus. I'm going to define it that way and call this V sub 6 amp. So we need to find that variable. We need to find the current through the 2-volt source. Once again, I can put the current in whatever direction I want. I'll put it going that direction, and let's call that variable I sub 2 volts. Then we need to find the current through the 6-volt source. I will arbitrarily put it in that direction, I sub 6 volt. Finally, we need to find the voltage across the 4 amp source. I will put the plus there and the minus there and call this variable V sub 4 amp. So notice, for every voltage source, we need to find a current. For every current source, we need to find a voltage. So the next step now is to use KVL, KCL, and Ohm's law to see if we can find these variables. So let's try to find I sub 12 volts first. The first thing we can do is we can use Ohm's law to find the current through this 4 ohm resistor. Because in the previous example, we found the voltage across it was 8 volts. So the current through this resistor is the voltage across it divided by the resistance. 8 volts divided by 4 ohms is 2 amps. So from Ohm's law, we can determine that I sub 12 volts, which is the same as the current through that 4 ohm resistor, is 2 amps. Notice, because the left part of the resistor has a higher voltage than the right part of the resistor, the physical current through the resistor goes in that direction, left to right, which is the same orientation as our variable I sub 12 volts. So I sub 12 volts is 2 amps. So from here, we can determine the power delivered or absorbed by the 12 volt source. So the power absorbed by the 12 volt source is the voltage across it times the current into the plus terminal. Since our current variable I sub 12 volts left the positive terminal, the current into that is negative I sub 12 volts. So we get minus 2 amps or minus 24 watts. So the 12 volt source supplies 24 watts of power. Next thing we want to find now is the voltage across the 6 amp source. So once again, we want to think about what we do and do not know already. So we're looking for this voltage here. So to find a voltage, you typically want to use Kirchhoff's voltage law. So if you can find a loop where you know every voltage except that unknown voltage, you can then apply KVL to find that voltage. The problem is we don't have any loops where we know every voltage yet, unless we look at this 2 ohm resistor and think about Ohm's law. We know the current through that 2 ohm resistor is 2 amps going up. So once again, from Ohm's law, we know that the voltage across that 2 ohm resistor is what? It's the resistance times the current, or 4 volts, and the orientation has to be what? Because the current goes from the bottom to the top, the higher voltage has to be at the bottom, and so we get 4 volts. We now have a loop where we know all the voltages except this unknown voltage V sub 6 amps. So applying KVL, we get 4 volts minus 2 volts minus V sub 6 amps is equal to 0. Basically, I'm going through this loop here. Solve, you get V sub 6A is equal to 2 volts. From here, we can now determine the power absorbed or supplied by the 6 amp source. So the power absorbed by the 6 amp source is the voltage across it, 2 volts, we just determined that, times the current entering the plus terminal. The plus terminal is on the left. The current is leaving the plus terminal, so the current entering the plus terminal is minus 6 amps. Using the passive sign convention, we get negative 12 watts absorbed. So once again, this also supplies power. All right, now let's find I sub 2 volts so we can find the power supplied or absorbed by the 2 volt source. So for this one, since we're looking for a current, something like KCL makes sense. If you remember the other day, we determined that we could not do KCL at this node here because we did not know the current through the right branch. However, at this point, we now know all the other currents except that one, so we can apply KCL at that node to find I sub 2 volts. Basically, we're saying that this current plus this current plus this current has to be 0. So using KCL, the current to the left we already determined was minus 2 amps. The current going down, we determined that the other day, that's also negative 2 amps. The current going to the right is a variable we're looking for, I sub 2 volts. The sum of those equal to 0. So solving, we get I sub 2 volts is 4 amps. Once we know that, we can find the power absorbed by the 2-volt source. The voltage across the 2-volt source is obviously 2 volts. The current going into the source is a current in that direction, which is negative I sub 2 volts. So we get minus 4 amps and we get negative 8 watts. So once again, this source also supplies power. Now, if we want to find the power absorbed or supplied by the 6-volt source, we need to find its current first. So once again, we think about using KCL. Once again, whenever you want to find a current, it makes sense to use KCL. So if you find a node, let's say this node here, do we know the current going to the left? Yes, because it's given. Do we know the current going up? Yes, we just determined that in the previous step. And this is a current we're looking for. So we can now apply KCL again. Current to the left is 6 amps. Current going up is negative I sub 2 volts. I sub 2 volts was 4 amps, so it's going to be minus 4 amps. Current going down is this new variable we're looking for. It is negative I sub 6 volts. Why negative? Because our variable as we defined it had the arrow going up, so we hit the arrow head first. So summing the currents leaving this node here, we get 6 minus 4 minus I sub 6 volts. That has to be 0. So this variable we just defined, I sub 6 volts, is 6 minus 4, or 2 amps. So we can now find the power absorbed by the 6-volt source. The voltage across the 6-volt source is 6 volts. The current entering the plus terminal is this current here, which is negative I sub 6 volts. And so we multiply this by minus 2 amps to get minus 12 watts. Finally, we have the 4 amp source. So we want to find the voltage across it. So V sub 4 amp. So we have a lot of choices here. At this point, we're almost done. We want to find the voltage across this 4 amp source so that we can find its power. So we need to find a loop where we know every voltage except that one. Well, at this point, there are many different options you can choose. I'm going to choose this loop here. So we'll do KVL. Starting at this point down here, we have our variable we're looking for, V sub 4 amp. And once again, because we're hitting our plus terminal first, we write it as plus V sub 6 amp. V sub 6 amps, we saw in this step here was 2 volts. So we add 2 volts. Then, as you continue to the right, we hit our 6-volt source. Sum of that is equal to 0. So once again, we're going through the loop in this direction, adding up voltage drops. We get V4 amp plus 2 volts plus 6 volts is equal to 0. So that means V sub 4 amps is minus 8 volts. So we can now find our final power. The power absorbed by the 4 amp source is the voltage across it. There's 8 volts across the source, with the higher voltage being on the top. So the power absorbed by the 4 amp source is its voltage, times the current into the plus terminal, which is going from top to bottom, which is the same direction as the actual current. So we now have a plus 4 amps. We get 32 watts. So notice this last source actually does absorb power. The other ones, because they're negative, they all supply power. So in this example, we basically saw that by introducing these new variables here, solving for those variables, and then using the power equation for each of the sources, we can solve this problem. But we also saw this is sort of disorganized. You don't necessarily know which step should you perform next, and you could conceivably get to a situation where you don't have another logical step. Now in this example, we were able to do it, and it wasn't terribly complicated, but the goal in this course is to find better ways to solve circuits. So this is the ad hoc approach. It can work in a relatively simple circuit like this. It did work. We were able to solve the problem, but it was not necessarily an organized way of doing it. So the goal over the next few weeks is to come up with more organized ways to solve circuits. And we're going to see there are 2 basic approaches to solving circuits. The first approach is using what's called equivalent circuits. The idea here is to use Kirchhoff's voltage law and Kirchhoff's current law to try to simplify a circuit by replacing parts of the circuit that you're not as interested in with an equivalent, simpler circuit. So some of the things that we're going to see that you can do, you can combine sources that are in series or parallel. You can also combine resistors that are series and parallel. We're also going to look at there's another technique called voltage and current division, which could be used to simplify a circuit. There's another technique called source transformations that we could use to simplify circuits. And then later on, not right away, but in a later packet, we're going to use something called linearity superposition and Thevenin's and Norton's theorem to simplify circuits. A general rule of thumb in solving circuits by coming up with equivalent circuits, a general rule of thumb is you only want to combine elements that you're not explicitly interested in if possible. And we're going to see this in some examples. So general rule of thumb is to only combine circuit elements that you're not explicitly interested in if possible. In other words, suppose you're looking to find the power absorbed by a resistor. You want to refrain from combining that resistor with other resistors because that's going to make it harder to find the power absorbed by that resistor. Likewise, if you want to find the power delivered by a voltage source, you do not want to combine that voltage source with other voltage sources because that's going to make it harder to find that power. We're going to see that equivalent circuits can effectively be used to solve a lot of circuits, but we're going to see also that it's not always the best approach. In some cases, you want to come up with very systematic ways to solve circuits without simplifying the circuits, and that's going to be nodal analysis and mesh analysis. Nodal analysis covered in the sections 4.2 to 4.4 of the book, and mesh analysis in sections 4.5 through 4.7. But for now, we're going to focus on combining sources, combining resistors, voltage current division, and source transformation. That's what we're going to be looking at now. So the simplest of these combinations is finding equivalent voltage sources when you have voltage sources connected in series. Suppose you have a whole bunch of voltage sources in series, so they share the same current, and they're connected up to part of a circuit. As far as the rest of the circuit is concerned, this blue blob is concerned, it does not know the difference between these individual voltage sources connected in series and equivalent single source. Turns out that this equivalent single source has the same value as the algebraic sum of the individual sources. You can get that result by doing KVL along that loop. You get minus V1 minus V2 minus V sub n plus V is equal to 0. So traveling through this loop, adding up voltage drops, solving for V, you get that this voltage V, the voltage at these terminals here, happens to be the algebraic sum of V1, V2, V3, V4, etc., all the way up to Vn. And so the equivalent voltage source is just the algebraic sum of those. Key term here is algebraic sum. If one of these voltage sources, one or more, is oriented the other direction, for example, maybe V4 has the plus on the left rather than on the right. So notice these other ones have minus plus, minus plus, minus plus. If that one has plus minus, you would have to put minus V4 in there. And a way to think about this is you think about the orientation of your equivalent source. Your equivalent source is trying to push current in that direction because that's how we have the plus. So any source that has the same orientation, you put a plus before it. Any source that has the opposite orientation, you put a minus. And we'll see this with an example. I am not saying that this circuit on the left is the same as the circuit on the right. What I am saying is as far as the rest of the network is concerned, the blue blob, they are equivalent. So if we were looking for information about this voltage source here, we probably would not want to combine all of these in series because you lose that individual source. However, if we're looking for something in this circuit on the right, combining all these sources together might make sense. You can also combine resistors in series and see that that's fairly simple as well. So once again, suppose you have a circuit, a network, connected to a whole bunch of resistors in series. As far as this network is concerned, it doesn't know the difference between the series connection of resistors and a single equivalent resistor called R equivalent. So let's find the value of that equivalent resistance. If we apply KVL here, we see that the voltage across this terminal of the network is minus V. So we get minus V plus the voltage drop across every resistor. But the resistors all have the same current I. So from Ohm's law, R1 has a voltage, R1 times I. R2 has a voltage, R2 times I, etc., etc. Here's Rn times I. And notice the plus is on the left of each resistor because the current arrow is going left to right. So if we do KVL, we get minus V plus R1 times I plus R2 times I all the way up to Rn times I equals 0. Solving for V, we get this expression here. We can then factor out the I. And then if we compare that to the circuit on the right, from Ohm's law, V is R equivalent times I. Since these have to be the same, R equivalent is just the sum of the individual resistors. So combining resistors in series is even easier than combining sources, because in combining sources, you had to worry about possibly subtracting some. In resistors, they're all going to be positive. So what we're saying here is as far as the rest of this network is concerned, it doesn't know if you have 1 resistor, 2 resistors, 5 resistors, 10 resistors in series. All that it knows is what the total resistance is. So if you have 200 ohm resistors in series, it doesn't know the difference between that and a single 200 ohm resistor. So let's use these two concepts to solve a fairly simple circuit. So here we have a circuit where we have 3 voltage sources and 3 resistors, and we want to find the current flowing through this wire up here, I. The idea here is we're going to simplify this circuit as much as possible and see if we can find I using Ohm's law. So what we're going to do is we're going to replace all the voltage sources by an equivalent voltage source. we're going to replace all of the resistors by an equivalent resistance. And then I, from Ohm's law, is just V equivalent over R equivalent. So R equivalent is the easier of the two. Here we have 100 ohm and 300 ohm resistors are in series. The 200 ohm resistor is also in series. Even though it's on the other side of the circuit, and even though there's this voltage source in between, it still shares the same current as the 100 and 300 ohm resistors. Remember, things do not necessarily have to be next to each other to be in series, as long as they share the same current. So our equivalent is 100 ohm plus 300 ohm plus 200 ohm, or 600 ohm. Slightly more complicated, but still pretty easy, is finding the equivalent voltage. So I am arbitrarily, in drawing this equivalent, I'm putting the plus on top and the minus on bottom. I don't know ahead of time which side of this voltage source is going to be a higher voltage, so I guess. I'm going to guess the top is going to be higher, and then if I get a negative number, all that means is that my guess was wrong. So what I do now is I look at every voltage source and I see, does it have the same orientation or the opposite orientation as my equivalent source, and that'll let me decide whether to put a plus or a minus. So V equivalent, look at this 8-volt source first. It has the plus on top and the minus on the bottom, so it wants to push current in this direction, which is the same direction as my equivalent source, so that should be a plus. This 2-volt source has a plus on the bottom and the minus on top, so it wants to push current in that direction, which is opposite of my equivalent source. So I put a minus 2 volts. The 3-volt source on the right, this is a little tricky. So when you first look at it, it has the plus on the top and the minus on the bottom, which is the same orientation as my equivalent, but because it is on the right side of the circuit, it's actually the opposite orientation. If you think about this 3-volt source, it wants to push current in this direction, which is the opposite direction of my equivalent voltage source. So it has to be minus 3 volts. So the equivalent voltage is 8 minus 2 minus 3, or 3 volts. Once again, voltage sources are a little bit tougher than resistors because you do need to think about these signs a little bit. Once again, it's totally arbitrary how I define my equivalent voltage source. But once I define it, I need to be consistent, and if I end up getting a negative number, all that means is that guess of where I put the plus and where I put the minus was wrong. Okay, at this point we're ready to solve this problem. So we see the equivalent voltage source is 3 volts. That means that we have 3 volts across this equivalent resistor here. We know that the current through a resistor always goes from higher to lower voltage, and it follows Ohm's law. So using Ohm's law, we get 3 volts over 600 ohms, or 5 milliamps. Is this the only way we could have solved for this current? No, but it's a fairly simple way. Basically, once again, we're using an equivalent circuit combining these 3 voltage sources in series, combining these 3 resistors in series, and then using Ohm's law to get our final answer. Let's look at things in parallel now. So let's start with parallel connected current sources. So let's assume we have a whole bunch of current sources in parallel connected to the rest of the circuit. As far as the rest of the circuit is concerned, it doesn't know the difference between all of those sources connected in parallel or an equivalent current source. It doesn't know if there's 1 source or 2 sources or 3 sources, etc. All that it knows is that there is some current being provided to it. So looking at this top node here, we can now apply KCL. Basically, this current plus that current equals 0. We get minus I1, minus I2, minus I sub n, plus I is equal to 0. Solve for I. we get this expression here. On the right, if you do KCL there, you get minus I equivalent plus I is equal to 0. So I is equal to I equivalent. Setting these equal to each other, we see that I equivalent is nothing more than the algebraic sum of the individual current sources. Key term here, just like with voltage sources in series, is the term algebraic sum. If one of these current sources happened to had the opposite orientation, let's say I sub 4, then we'd have to subtract its current source value. So when you find the equivalent current source, you basically arbitrarily give an orientation to your current source, and then you look at the individual current sources and see whether they have the same orientation or the opposite orientation, and that dictates whether you have a plus or a minus sign. Like voltage sources in series, I am not saying that this circuit on the left is the same as the circuit on the right. What I'm saying is, as far as this part of the circuit is concerned, they are the same. If we are interested in one of these individual current sources, we may not want to combine all these current sources in parallel because you lose that individual information about the current source. If, however, we just want to see the effect that these current sources have on the circuit on the right, it's okay to combine these. Let's talk about combining resistors in parallel now. So once again, let's assume we have a circuit here with a whole bunch of resistors in parallel. So they have the same voltage across them, call it V. If you take that same circuit now and put a single equivalent resistance across it, this network does not know the difference between all of these resistors in parallel on the left and a single equivalent resistance on the right. So we need to determine what that equivalent resistance is. So let's apply KCL at this top node. Current to the left is minus I. The current through each resistor from Ohm's law, since you know the voltage is V, this current is V over R1, this current is V over R2, etc., all the way up to V over R sub n. So minus I plus V over R1 plus V over R2 all the way up to V over Rn is equal to 0. Solve for I, you get that. We can then factor out the V to get this expression here. If we rewrite this expression as V as a function of I, we get that this part here becomes a reciprocal, and we get V is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn times I. Now let's look at this equivalent circuit on the right. From Ohm's law, we know that the voltage across R equivalent is equal to R equivalent times this current I. If we now set this equal to this, we see that this expression here has to equal R equivalent. So we have our final expression that when we have resistors connected in parallel, the equivalent resistance is the reciprocal of the sum of the reciprocals of the individual resistors. So let's say that again. R equivalent is a reciprocal over the sum of the reciprocals of the individual resistors. So you have to take the reciprocal of each resistor, add them all up, and take that reciprocal. So you have to take a reciprocal multiple times in this equation. So it's clear that resistors in parallel have a much more complicated equation than resistors in series. In series, you just add them up. In parallel, you have to take a whole bunch of reciprocals, then add them up, and then take a reciprocal at the very end. So it takes a little more work than resistors in series. Turns out that if you just have two resistors in parallel, the equation gets a little simpler. So two resistors in parallel, the equivalent resistance is 1 over R1 plus 1 over R2. Let's multiply that by R1, R2 over R1, R2. This is just 1, so we're just multiplying it by 1. So the numerator now becomes R1, R2. The denominator, R1, R2 over R1 gives us R2. R1 times R2 over R2 gives you R1. So the denominator is R2 plus R1 or R1 plus R2. So we see that when you have just two resistors in parallel, the equivalent resistance is the product over the sum. By the way, that does not work with 3 or more resistors. If you have 3 resistors in parallel, you get 1 over R1 plus 1 over R2 plus 1 over R3. You work that out, it's actually this relatively complicated expression here, which is not the same as the product over the sum. So notice it's a product over a sum of subproducts. R2 times R3 plus R1 times R3 plus R1 times R2. This expression, although it's true, is probably not worth memorizing. It's a little complicated, and with 4 and more resistors, it gets even tougher. So bottom line, for 2 resistors, it's probably worth your while to memorize this shortcut, the product over the sum. For 3 or more resistors, it's probably not worth it. Let's talk about a couple other shortcuts. Suppose you have 2 resistors that are the same and they're in parallel. And by the way, for parallel, we use this symbol here, meaning they're in parallel. So you would read this as R in parallel with R. Turns out that R in parallel with R, using this expression above, would be R squared over 2R, which is just R over 2. So this is probably worth memorizing. A resistor in parallel with itself basically has half of that resistor value. By the same token, R in parallel with R over 2, plugging that into the expression above, you get R squared over 2 over R plus R over 2. That's R squared over 2 over 3R over 2. You get R over 3. Likewise, R in parallel with R over 3, following the same math, you get R over 4. In fact, you get this general expression, R in parallel with R over X is R over X plus 1. So for example, a 20 ohm resistor in parallel with the 2 ohm resistor, you could do the math either this way or this way, but you can also use a simplification. This is R in parallel with R over 10, which becomes R over 11. 20 over 11 ohms. So bottom line, it's probably worthwhile to memorize this expression. It's certainly worthwhile to memorize these shortcuts as well. Turns out, for resistors in parallel, you could get a simpler equation if you use conductances rather than resistances. If you remember from Ohm's law, V equals I times R, or I is G times V, where G is a conductance. So it turns out that this current is V times G1, this current is V times G2, this current is V times Gn. So if you were to do KCL at this node, do that current plus that current plus that current plus that current, you would get negative I plus VG1 plus VG2 plus VGN is equal to 0. Solving for I, you get I would equal to G1 plus G2 plus G3 plus G4, etc. All of that times V. Then, of course, if you had this equivalent circuit here, we would know that I is equal to V times G equivalent. So setting these equal to each other, we see that G equivalent is G1 plus G2 all the way up to Gn. So an alternate form of resistors in parallel is that the equivalent conductance is the sum of the individual conductances. Individual conductance is just a reciprocal of the resistors, and once you have G equivalent, to get R equivalent, guess what? You have to take another reciprocal. We still have the reciprocal of the sum of the reciprocals. You have to take the reciprocal of each resistor to get the equivalent conductance. And then you take the reciprocal of the conductance to get the equivalent resistance. We're back to this equation here. So although it might look like working with conductances is easier than resistances, it really isn't. So what we've done so far is we've looked at voltage sources in series, resistors in series, current sources in parallel, and resistors in parallel. Now you might ask, what about voltage sources in parallel? If you remember from a previous lecture, that is a no-no. You do not have voltage sources in parallel. You violate KVL if you do that. Likewise, you don't have current sources in series because that violates Kirchhoff's current law. So we will pick this up next lecture and do some examples showing how we could use these voltage and current source combinations and resistor combinations to simplify a circuit, and then we'll see that there are some limitations to that. Have a good day.